So hello everyone, I'm Ming Yang. So today I'm gonna introduce our new work PRMBench here. And the full title of this paper is PRMBench, a fine-grained and challenging benchmark for process level reward models, which is a simple title and directly describes what we have done in this work. And fortunately, our work has been accepted as a conference paper at the ACL 2024-5 and we'll be there to present our work in person. And our poster will be at July 28th from 11 to 12:30 at Hall 4 or Hall 5. So I'm looking forward to meet you guys at the conference center and want to communicate with you guys in person. Yeah, so please come and communicate. Yeah. So today, I will introduce from these five aspects. So first, I will introduce our direct motivations of this work, and will give out our detailed methods and our experiments and the main results, and we'll give out an example of our test case, and finally, we'll give out our analysis and the most important takeaways. Yes. So. Our direct motivation is that we found that the large reasoning models tend to generate unreliable reasoning process. So in this picture, the left part is the spurious proof of the three-dimensional mean value theorem generated by OpenAI O1. So in this question, we ask the OpenAI O1 to prove the three-dimensional format of the MVT. But we all know that MVT cannot be applied at the three-dimensional scenarios. However, the O1 has generated the reasoning process, and it is obviously incorrect. But we want to find that in which step it generates an incorrect reasoning process. So we found that in step 2 and step 5, it uses and applies MVT into this process. So we can make it sure that the step 2 and step 5 is incorrect. And subsequently, we want to see that whether the PRMs or the process level reward models can identify these errors in this case. So we select two popular PRMs and test them on this case. So obviously, it cannot tell all of the error steps here. So we found that the PRMs and critic models are not able to identify all these error types precisely. Yeah. And I think that the fine-grained PRM benchmarking is still underexplored for now. So these are the direct motivations that we propose a PRM bench. So our main contributions can be listed as these four items. So the first, we present the PRMBench. It's a first comprehensive benchmarks for PRMs, and it covers the three carefully crafted evaluation categories and 9 subcategories, ensuring a fine-grained evaluation. And thirdly, based on our proposed PRMBench, we conduct the in-depth pilot experiments on 25 models, including the PRMs along with the SOTA critic models. Yeah. So and finally, to facilitate future research, we release the PRM Evo Toolkit, and this offers an automated evaluation framework for PRMs and customizable data generation system. Yes. So our main method can be demonstrated in this main figure. The left part mainly displays our data curation procedure. So we select PRM 800K as our data source because it offers extensive reasoning process data and step-level data labels. And based on this PRM 800K, we use category-specific prompts to get the GPT-4o in generating a lot of reasoning steps along with their corresponding labels. Through this procedure, we can get the step level data. Yes, And above all, we conduct the quality control procedure to make sure the overall data quality. So the quality control can be divided into two steps. The first step is feature filtering. So we employ the rule-based filtering to exclude the data that fails to satisfy the structural constraints. And secondly, we use human verification. We employ some volunteers and check the 10% of the PRMBench. And the check shows that over 92% of correctness and 98% of difference qualification rates. So it's quite okay. Yeah. And as mentioned in the category-specific prompts, we also design some evaluation categories. So mainly it can be divided into simplicity, soundness, and sensitivity, three big categories. So the simplicity mainly evaluates whether PRMs can detect the redundancy scenarios, and the soundness mainly assesses whether PRMs can detect the erroneous within the reasoning process. And the sensitivity category mainly inspects PRM's robustness to details such as the critical conditions or implicit requirements. Yes. And each domain is further divided into the detailed subcategories for more fine-grained evaluation. Yeah. Here we give out us an example. So our data test case is somehow like this, right? It's so many reasoning steps with their labels. So in this case, we can see that in the step 6, we can see that it's a product, right? It's a product. But in step 9, it is formulated as an add-on. So it is obviously incorrect here. So we'll give out the labels of each steps, and we utilize all of the PRMs and critical models to judge whether each step is correct or not, and we will get the final score here. So here is how we evaluate the PRMs and critical models. Yes. And we have done our experiment on over 25 models, including the PRMs and the critical models, and we found that first we found that the PRM has partially grasped the multi-step process evaluation. We found that even the SODA model still underperforms human evaluation. Although PRMs undergo a dedicated training process, and most of them still fail to match the performance of the general purpose language models, which we call the critical models. Yes. And secondly, we found that the simplicity is more challenging for PRMs. For instance, in the sensitive category, the reason evil performs relatively well, but its performance drops at the simplicity category. Yes. And above all, we propose a PRMBench STEM. So we also curated some data from the STEM focused data such as biology, chemistry, and physics to curate our PRMBench STEM and evaluate models on it. We found that it has a lower PRM performance compared to the PRMBench, the math version of the PRMBench. Yes. And in the PRMBench STEM, the simplicity is still most challenging. Yes. And here we dive into the analysis. So here we give out four important takeaways. So the first takeaway is that we found that PRMs show a clear bias during evaluation, often favoring positive rewards. So here we divide the whole evaluation set into the positive subset and negative subset. The positive subset contains all of the step labels that is assigned as a positive label, as correct label or something. like that, yeah. And the negative subset is the all of the reasoning steps that is assigned as a negative labels. So we found that the positive subset, uh, uh, the models performs relatively good as a positive subset and relatively poor as a negative subset. So this indicates somehow bias. Somehow it indicates model has prefer to answer a positive answer or answer yes to the question. So and subsequently we calculate the similarity between the ground truth and the process that contains errors and that contains curated errors by us. Yes, so we calculate the similarity here. So we can observe a relatively higher similarity over the random guess. So this means that the model has a poor differentiation between the ground truth and the error containing labels. Yes. So second takeaway is that we found that PRM show a gradual improvement in performance as the position as the steps increases. So in this picture, we display the correlation between the step and the accuracy. Here we can observe an increase of the PRMs, the blue bars, the PRMs. It can be observed as an increasement, but the critic models or closed-sourced large language models, it performs relatively stable. Yes. So the third takeaway is quite simple. Is that we found that in-context learning has subtle impact or even no impact on the model's performance on PRMBench. So the last takeaway is that we found that PRM struggle with detecting false positives, exposing the potential for reward hacking. So here we compare the evaluation of PRMs on BON, the best of N, and our PRMBench. So we all know that best of N is a evaluation method that based on outcome level data, right? So we mainly observe two metrics: is the standard deviation between the BON and our PRM score. We can say that of BON it has a relatively lower deviation parameter, but when it comes to PRM score, it has a relatively higher. So I think this might indicate somehow the PRM score is more differentiable. And the BON detection is less differentiable among these models. And subsequently we calculate the Somers D correlation parameter between the BON and the PRM score. So this is a comparison between the BON and the PRM score, the Somers D correlation. So we can observe a relatively low Somers D correlation parameter. So this indicates that it is inconsistent. It is somehow inconsistent between the PRM score and the BON evaluation. So it indicates the inconsistent between the outcome level evaluation and the step level evaluation. So this indicates a false positive situation and a step level reward hacking situation. Yes. So this takeaway might be the most important takeaway in this work, I think. Yes. And that will be all. So thank you guys for listening. And again, our post time will be at July 28th from 11 to 12:30 at Hall 4 and Hall 5. I'm looking forward to talking with you guys. So thank you. Bye bye.